This is the video 10 of the Thermodynamics course with Lars Erik, and this video is about a general proof of the connection of the definition of partial molar property, with that this actually means that the total amount of the property is the sum of the amount of each component and the partial molar property. And a general proof with several components in textbook. Page 384. So this is the general, and here only for a binary if we again make a sketch where we have the mole fraction from 0 to 1. And we have the property of component 2 at the left, and the property of component 1 at the right. And if we draw a curved line, that is the property. If things were ideal, we would have the ideal as at this line, but we are talking about a general property, and that is not necessarily linear. In this case, it is curved with the mole fraction, and if x1 is 1, that means we have pure component 1 here. So this is the property for pure component 1, and this is the property for pure component 2. And if we take one mole fraction in the picture, then we can draw a tangent line. This is a tangent, and we get the partial molar property of component 1, or I1, and here we have partial molar property of component 2, which we can call I2. The total property is I2 plus I1 plus I2 times the mole fraction. That is that one. If we multiply nm equal to n1 plus n2 times I2 plus I1 plus I2 times n1. I have just multiplied that equation with the total amount of moles. And then we take the derivative of the total property and keep pressure, temperature, and all other components constant. Then we get I2 plus I1 minus I2 equals to I1. This is that one. That means that this partial molar property must be equal to this I1, which is the tangent when it passes 1.0. And by symmetry, the partial molar property of component 2 is I2 by symmetry. Or we could have done exactly the same for component 2. And M is M2 plus M1 minus M2 X1 and N is N1 plus N2 M2 plus N1 minus N2 N1 or Nn is N1 times the partial property of N1 plus N2 times N2, the partial pressure, the partial property of that. So this is one result, and this is the partial pressure, partial property of the component. So what we try to prove is that we have this connection that if we define the partial molar property this way, that is equivalent to state that the total property is the sum of partial molar property times the amount, and this is in a way shown graphically here, and this is shown mathematically here by defining the partial molar property and ending up with this connection that the total amount is the Nm times the partial molar property of component 1 plus N2 times the partial molar property of component 2. So this is the end of video 10. This is video 9 in Thermodynamics with Lars Erik, and this is about solution thermodynamics theory, and it is from chapter 11.3, and it is a summary of partial properties. The most important is to define the partial molar property, which is the derivative of the total property, which is the number of moles times the property by Ni. And we keep the pressure, the temperature, and the number of moles of all other components constant. And we have, this is general for any component, and we have, in my point of view, the most easy to understand, which is the volume. Among these thermodynamic properties, volume is the simplest to understand. The change in total volume by the change of the amount when pressure, temperature, and the amount of all other components change. This means we could be even more formal to say that Nj is all components not equal to I. So that is the same notation. And then we have this equivalence that when we define the partial molar property this way, this is equivalent to state that the total volume, N times the molar volume, is the sum of all components Ni times. So we can have one there and one there. So those two equations, they are equivalent. You can deduce that one from that one, or the opposite direction. In general, Nm is the sum of all partial properties times the partial molar property. And for 1 mole, we can replace the amounts with the mole fractions. And especially we have that the Gibbs free energy partial property is dmg dmi p, t, and mg constant, and that is the chemical potential. And for equilibrium, especially for vapor liquid, the chemical potential in the vapor is equal to the chemical potential for the liquid. And this is for all components. So this is the definition equation for the special case of volume. This is for volume, and this is equivalent with the total property as the sum of the partial properties times the amount of each component. When we define a partial molar property for Gibbs free energy and give a symbol of this called the chemical potential, then we achieve an equilibrium criterion stating that the chemical potential in the vapor must be equal to the chemical potential in the liquid for all components. The symbols we use volume, energy, enthalpy, entropy, and Gibbs free energy. And we have a general symbol M for any property. We have partial property. And this is the symbols used. And also for property. And we have there are different ways to use symbols for pure components, but in the textbook, and I will also use VI, UI, HI, SI, GI, and also MI for the pure component, and these are symbols for the partial properties. The most easy to understand is probably the volume. We define the partial molar volume as the change in total volume with the change in the amount of the component with PT and the amounts of all other components constant. And we have graph. This is figure 11.2. In cubic centimeter per mole. This is the volume. This is the mole fraction. And to the left we have pure water. To the right we have pure methanol. And we have 20, 30, 40, and 50 cubic centimeter per mole is a quite easy measurable quantity. The volume is easy to measure, and if we have one value here and another value here, we have a straight line here. The volume of methanol is 40.73. The volume of pure water is 18.07. And if we make this curve, it looks about like this. and we can take one point at x equal to 0.3, and if we take a tangent in this point, we can read the partial volume of methanol in that point. That is 38.63. And if we take the tangent down here, we find the partial molar volume of water at 0.3. That is 17.77. So this is an illustration for the volume. We can measure the volume as a function of mole fraction, and if we have pure components, it is easy in literature to find these values for pure component water and pure component methanol. And if we make a tangent through this point of x equal to 0.3, we can use this equation to convince us that this straight tangent going through the point 0.3, that will be the volume in that point, and the partial molar volume at this side will be 7.77, which is lower than the pure component volume, and the partial molar volume of methanol is 38.63, which is also lower than the pure component methanol. So this should be a summary of partial properties, and we will go more into details about these things later. So this is the end of video now.